Hey guys, today we want to learn about bonding, how atoms connect to each other, right?
I think so.
So, turns out there are three main types of bonding. Now, this may be reviewed. So, Mr. Mitchell, what are the three types of
Well,
bonding?
we've talked about this before, but one of the ones we focus a lot on are ionic.
Ionic, okay. And then there is covalent.
Well,
Or metallic. Whatever you want to write next.
I'm going to write metallic down.
We'll do metallic next. And then we'll do covalent.
Yeah.
All right.
So,
Ionic.
As you can see, we clearly are following the script.
What script? So in an ionic bond, it's a bond between a...
Metal, which is, remember our
the
little
metals are everything to the left of my ruler, so to speak. And the non-metals are upper right. Now, we've learned how to name these. Iron 3 chloride. Also includes like polyions, like iron 3 phosphate, things of that nature. So ionic are those bonds. And then the second one is, so make sure that you write that down, metal to non-metal. And metallic bonds?
Well, metallic's weird because we call it a bond, but really a metallic bonding occurs with a metal and more of its own kind.
So like copper with copper.
Yeah, so if I have copper, let's say right here, a piece of copper metal, what that really is trillions and trillions of copper, but they actually hold on to each other in a kind of a unique way that we're going to talk about in a bit.
And yeah, like my copper ring, right? My gold ring. I guess this is gold.
Holy cow, if you have a copper ring, your wife did not care.
Let me start over. So I've got a gold ring right here. So this is the element Au right here. So it's gold connected to gold connected to gold. And then lastly, there's the covalent bonds, right?
Yeah.
And that's between what and what?
Two nonmetals. So again, that little staircase becomes kind of big for us, right? Because
These guys connect to each other plus hydrogen.
yeah, hydrogen's kind of a
All right,
traitor.
so let's go deeper with ionic bonds. So in an ionic bond, the classic example of ionic bonds is sodium chloride, salt. You played around with salt. Sodium, if you think about it, right? Let's go back to our table, guys. Sodium is in column number 1, so he has one valence electron. Now I'm going to do something you've never seen before. Just break the periodic table. No, I'm going to put a dot next to sodium. That dot represents his one valence electron. And then I'm going to draw chlorine, and I need to figure out how many valence electrons he has. So if we look at chlorine, Mr. Demetriou, it's in this column here, column 17. So what's the deal on the valence electrons?
Well, skipping the middle block here, we typically count 1, 2, 3, 4, 5, 6, 7, 8, and that represents the number of valence electrons.
So this would be
7.
So in that case, what I want to do is for the chlorine, I'm going to put 7 valence electrons represented by 7 dots. And remember that all atoms want what? What's the deal?
Full outer shell of 8.
So they want 8. 8's the magic number. Now, sometimes you say, wait, for him to get 8, sodium, he's got to gain 7. But there's another way to make him happy. What is that?
And that's, you can lose electrons. And we talked about this before, so this is nothing new to you. But this can lose. Remember we talked about an ionic bond being one atom stealing electrons from another? And that's essentially what's happening here. Chlorine's going to steal that electron.
So it really has 8, but 8 in the previous shell, right? And so what happens if we redraw the structure, when the sodium loses his one valence electron and has no valence electrons, or technically 8 in the previous level, his charge becomes positive. Because if you lose something negative, you have a positive charge. And then the chlorine, who now has 8, maybe I'll put an X here to represent the electron that came from the sodium. Since he has one more electron, his charge is -1. Now, why is that important when we talk about bonding?
Opposites attract. Remember that, young ladies, when you want to talk about dating the biker dude when that's 35.
Don't do that.
I just sent a chill through my body as a father of a daughter, and I'm sure yourself as well. So what we have here is we have a positive and negative, and positive and negatives, they just attract.
Yep.
Always. So if I have a positive right here and a negative right here, these are going to attract each other. But here's the thing that we have to keep in mind. We never have one sodium and one chlorine just wandering around like, hey, how you do? How you doing? How you do? How you doing? How you do? How you doing? And interacting. That doesn't happen. It really happens with trillions and trillions of these guys happening all the time.
So if you're looking at a tiny grain of salt, you're looking at trillions of sodiums connected to trillions of chlorides. And here, in fact, is salt itself. If you look at this carefully, this is halite. Halite is, so this is just a big piece of salt. And this is more than trillions, because this is a big, big piece of salt, gazillions of sodiums and chlorides, and they make this thing we call a lattice.
Yeah, lattice are,
yeah,
so here's the thing, if I'm this positive, do you realize that all negatives are equally attractive to me, right? So if I have this, let's pretend that another sodium and chlorine do the exact same thing that we just had happen here. We could have this happen. We could have a negative formed here and a positive formed here, and wouldn't these two attract each other just like we just drew?
Yeah, but wouldn't they attract
But
each other?
now, this positive and this negative, I mean, if I'm in this positive, this negative is equally attractive to me as this one is.
And like this pattern continues on and on and on, billions and trillions and quadrillions of atoms long to make this piece of halide.
And by the way, one of the things that is really important, and I kind of gotten lazy with drawing the positive and minuses, I'm going to do them right now, is that it's also three-dimensional.
Yep.
So we also have NAs and CLs that are coming out of the board. So this right here, if we were to shrink it down, we're talking about infinitely smaller, which is why that particular rock right there is quadrillions and quadrillions and quintillions of ions together.
Yeah. So now that leads to some interesting properties of ionic compounds. So ionic compounds, actually, first of all, I know they have a name besides ionic compounds. What's that name?
Yeah, we call it generically salt. It's kind of weird because we've talked about table salt, NaCl. We call that salt, and that's our only salt. But every single ionic compound is a salt.
So if I have magnesium phosphate, a metal, magnesium bonded to the non-metals, the polyion phosphate, that is called a salt.
It's called a salt. Now the other thing is this, when these things hold on to each other, they hold on to each other very, very tightly. And in order to like maybe separate them out or move them, you have to actually break bonds, which means that all salts are really, really brittle. If I wanted you to break that, would you be able, yeah, you'd have to smash it. Would you be able to take it and bend it to your will?
Can't do it.
And if you imagine, if you would, even a tiny piece of salt, so that's obviously too big for, and it's too many of these interactions. But if you had a single grain of salt and you're like, I crush you, you could squish it and break it apart. It's not going to bend. No. Ever.
So it's got a property that we call it's brittle. So it turns out that most ionic compounds are brittle, right? So you're going to find them to be brittle. So take a hammer and smash it. You could smash this. What other properties of ionic compounds?
Well, one of the things we really care about a lot of is whether or not things are good conductors of electricity.
Now, what does that mean, conductors of electricity?
What that means is that electrons can flow through them. Because all electricity is, and when you flip on your light switch,
it's electrons.
Yeah, it's electrons that are passing through your core and then coming back through. That's why we have two prongs.
And you know that you probably never would do this. You never take like a metal object and stick it into an electrical
You're just saying to them, now we have the psychos in our group.
Never
that
ever do that.
Don't do that.
That'd be very bad. But this right here, sodium chloride, is not a conductor of electricity. So it's considered a insulator as opposed to a conductor. So another thing you would say here is they're insulators of electricity.
Now, you should be aware of this here. These ions, these positive and negatives that are locked into space here, they can't do very much. But if we were to liquefy it, and by the way, all things have three states of matter, solid, liquid, and gas, they would now have positive and negatives that are randomly...
Yeah. So if you melt this, so you can melt this, it's like 3,000 degrees.
It's kind of hot, yeah.
Crazy hot. You can make it, and then it would conduct electricity, and then you stick your finger in there. Of course, you'd burn at the same time as being
it'd be a bad day for you all
together.
The other thing you can do, and you've probably done this before, because who doesn't enjoy a good cup of salt water, but if you take a chunk of salt and you throw it into water, all the ions will break apart. In fact, it'll dissolve completely so that you can't even see that you're drinking salt water. Super fun trick to play on your family members. Don't do that either. But if you now have ions in there, that's a really good conductor of electricity.
Yeah.
So we just talked about ionic bonding, right?
Yeah,
Let's talk about metallic bonding,
which is gold ring,
which is or copper, as we sometimes call it. Metallic bonding is really just metal ions interacting with their electrons. So let's take copper because that's a pretty good example. Yeah. So let's say I have a copper, and I'm going to draw a number of coppers all next to each other, and I'm going to draw them in two rows representing trillions. So in your mind, this represents trillions.
So here's kind of the thing that you should know about all metals, and you know this, is that metals are good conductors of electricity. That means electrons can flow through metals. That's why when you stick a piece of metal in an electrical outlet, it's a bad day. So that's something that if you know that about metals, that tells you how they're held together. It still comes back to the simple idea that opposites attract.
So right here we have, each of these coppers has a positive central nucleus. They also have electrons, valence electrons in particular. Now what's different about these, it's kind of like living in a commune, where, or being in a Ukrainian background, which is I come from, right? So when you're in a Ukrainian family and you have every instance of Thanksgiving, whatever, you have like 15 families, every aunt and uncle is your parent. They can all discipline you, they all have parental rights over you. It's a terrible way to live. Being a Ukrainian, I can say that. And the same thing happens here. This electron right here that originally belongs to this copper is free to move around. And it can go anywhere it wants between any of these metal ions. Similarly, this guy right here, and every time it passes through one of these guys kind of take care of it. So it holds it really, really tightly, which gives the property of metal. Like try and pull a metal piece apart. We talked about this way back. They have high tensile strength. You can't. But also what Mr. Bergman was saying, and this is kind of cool, yeah, he's going to demonstrate how he cannot pull his very, very solid gold ring apart. By the way, we did this, I think, before in my class. Take a thin piece of aluminum wire. Even the strongest of you cannot pull that apart. So these guys hold on really, really well. But each one of these negatives, they are free moving. Well, isn't electricity free moving?
Yeah.
And the fact that it's free moving means that if we were to plug this piece of copper in, aka a plug, into an electrical outlet, the electrons could then freely move through this. The other thing you need to look at is, see how these electrons are all kind of moving through this? And look at my hand motions here. It looks kind of like a sea, kind of like an ocean. So they actually call this the electron sea model. Sea as in ocean model, because the electrons are free moving. Now, doesn't that talk to us about all the other characteristics of metals?
Yeah, and you might even think of it this way: is what essentially happens for just a brief moment. Maybe more electrons are on this side of this, all these millions of copper atoms, which then by definition makes this side positive. Then you have a charge differential, positive to negative, which causes them to attract to each other, which is what holds metals. So,
All right, so one of the characteristics of metals is that they're bendable, they're malleable.
So this piece of copper, right, and I can bend it. Right, it's bent. I can bend it. So malleable means it can be bent. Okay. There's another tool or a feature we call it's ductile. That means you can pull it, or we say draw it into a wire. Same metal right here is I have a copper metal, and they pull it into thin wires. This is the kind of wire that you would use to put electricity in your house or wire your house up. So here, yeah, Mr. Dimitrievich, it's malleable, ductile. It's highly tensile, means it's very difficult to pull apart. It's a conductor, which is kind of that's the base thing. Because you can get this, you understand everything else. And of course, all metals have they all have a silvery colored thing. So here's a MacBook, right? This is aluminum, all right? So this piece of aluminum is silver in color. So all metals are silver with just two exceptions. And we happen to have them right here. My gold ring and this piece of copper.
Now, the interesting thing, and this is really important, this electron sea model is the reason that all of these other characteristics apply. So as long as and it's kind of weird because bonding we typically have associated with two different types of atoms. With metals, if you just see a metal just stand there by itself like a piece of copper, that's actually undergoing metallic bonding behind the scenes.
Because there are bazillions and bazillions of copper atoms connected, and there's these electrons roving around your Ukrainian family deal, going around all the time, and that's what's holding this together. Next up, we want to talk about the third type of bonding, covalent, because it's a little bit more complex and it's got all kinds of rules, but you'll get that then.
We'll see you then.